what is this thing called force? Well, apparently the mathematicians in the last 50 years at least, a little more really, discovered four forces. Just like the four horses of the apocalypse, they discovered four forces. Okay, what are these forces? Well, we go to a prominent site, and that's Eric Weinstein's and the Wolfram site, right? And they have all the information you need if you want to do math viz. And I just want to point out that there's four forces: the strong, the electromagnetic, weak, and gravitational. And they have what they call carrier. We have the carrier of a force. Okay, and what they do is, they have this little ball that carries interactions. It carries verbs, okay? And when the carrier for the strong force is the gluon. It mediates, between two quarks, allegedly pulls them together. How it does that, I don't know, because if it's a particle, you wonder how it carries the force of attraction, whatever that means, okay? The photon is the particle of the electromagnetic force, otherwise known as light, okay? And then we have the bozos. We have the bozos, the clowns, and that's the weak force, the W's and Z's, okay? And then a famous graviton, which they're still trying to figure out. They've never were able to pinpoint the graviton, and they never will because there is no such particle as a graviton. But they want to explain attraction by throwing a little ball known as a graviton. How do you do that? And yeah, they say that it delivers negative momentum. So instead of pushing you away, it delivers negative motion towards you. You can do anything in math viz, okay? Okay, so here are each one of these particles, okay, the forces. Here's the strong force. Says the strong force which binds the nucleons in the nucleus and the quarks with the nucleons. In other words, it's this strong force is inside the nucleus of the atom, and what it does, it keeps the quarks together that form the neutrons and the protons. Okay, so that's their job. And what you'll see is something where they cheat, because they have this particle, this gluon, and it stretches. It stretches, and they always illustrate it as a bubble gum, the stretched bubble gum, or what is it, a bed spring. So they have to stretch it to show that there's this tension, between the quarks. Yeah, they have to do something like that. They have to put an elongated object between the two quarks, because otherwise they cannot show how one quark physically attracts another. And so they always stretch the quark, and they put it as a bed spring or bubble gum or who knows what. Okay, so that's the gluon, the strong force. Okay, now here's the the electromagnetic force. Says it's a infinite range attractive or repulsive force which acts between charged particles. So it looks like the electromagnetic also is repulsive force. Okay, according to these people, and they see them as particles. The photon is the representative, is the carrier of this interaction, and you'll see a lot of that in the Feynman space-time diagrams. They always talk about that nonsense there. They like to put that's what he got his Nobel Prize for, by the way, the nonsense of space-time diagrams. Okay, and then we have the weak force, and that it says it transforms an up quark to a down quark. So it changes a proton to a neutron and vice versa, I guess, right? So that's this force, this particle, a W, a Z. I don't know what it looks like. I've never seen one of these particles. They never illustrated any of the particles in the standard model, so you have to use your own imagination what they look like, or whether they have shape, because they're really not talking about, they're not talking about a little ball. They represent it with a little ball, but immediately they go and talk about the energy and the the speed and the size and the mass and charge and all that other stuff. They don't talk about what does it look like. Well, it's a particle, Bill. It looks like this, like a little ball. That's what it looks like. Yeah, very simple. Okay. And then in the last one here, we have the graviton, okay? And what is the graviton? Well, they're still looking for it, but it's some kind of ball, okay, that produces attraction between, at least, in this world, I guess, why a pen falls to the floor. I guess the floor throws gravitons on it. They don't like to use the graviton for space stuff, cosmic stuff. That's when they replace that with space-time, okay? Because if they put particles there, they would have a lot of trouble explaining, the mechanism to a layman or even to themselves. So they don't use it there. Okay, here we have the problem. One of the problems with all these particles is that they all travel one way. Okay, the electromagnetic, graviton, gluon, and WZ bosons, they all travel one way. And that's already a handicap because, in order for you to have, some kind of interaction, the other guy has to shoot the same particle in the opposite direction. Hopefully the particles don't force, right? Don't collide. And one has to shoot at the other. So how that produces attraction is the problem, because we can understand forces like the photon, which is an outward force, always goes out, no problem there. Push. And then we have, the weak force, also a push, it goes outwards. But the gluon and graviton are pull forces. They pull things in, they produce attraction. That's their job, that's what they're supposed to do. How do you do that with a discrete particle? How do you throw a stone and have the dog come towards you? Right? That's the question. And no, you're going to have trouble with the mechanism. That's why they can't explain at least the graviton. And in the case of the gluon, they cheat. They put a bubble gum or a bed spring. Okay, so here we have one of the issues that Wolfram brought up in Eric Weinstein. And what does he say? He says, look, there's also a fifth force. So we had pull, push, perhaps, maybe, and now we have, I don't know what the fifth one is, what they call the fifth one. They call it the fifth force. Okay, that's good enough. And so they say, yeah, that they said there's some things that they cannot explain, some movements there that require a fifth force that is not one of the other four. And so they say, well, maybe there is a fifth force, and they're going to do an investigation. And remember, this came out in 1996. So since then, they've been looking for this fifth force. I don't know if anybody ever worked on this, okay? But they mentioned it at the time. We're talking about almost 30 years ago, right? And a few days ago, they went with this fifth force that I talked about the other day. But this is a different type of fifth force. This has to do with the muon, okay? It's got a little wobble that they cannot explain, and now this is a hot item right now. Everybody's looking for this fifth force. Okay, they're try to verify it so that they can win a Nobel Prize. So they say, oh, we found a fifth force, and it's the force that produces the wobble in the muon, which is unexplained by any other force. Okay, that's more or less their reasoning. So they keep inventing all these forces. Okay, so what does Weinstein say that a force is? I mean, what is a force? Okay, and so he goes in there and he says, look, a force is a push or pull. Okay, we're going to stop there. Pull, period. Punkt. Okay, it's a push or a pull. That's it. That's all the only type of interactions that we can imagine. Okay, so if you have contact with something, you either push or pull it. There is no other form of contact that we can imagine. So how do they come up with four forces? That they're all particles, right? And they all move one way, so we cannot produce attraction because they all move in the opposite direction to attraction, right? And he says it's a pull or a push. That's only two forces. How do they end up with four? So we got a little bit of problem because there's a mismatch there. He's telling us that it's push or pull, and then he comes up and says, oh, there's four forces. So one thing doesn't match with the other, okay? So we say, okay, what is a particle? I mean, how do you represent the force with a particle anyways? But they say it's the particle of force. And we call this one the particle known as the graviton, the other one is the photon, the other one is the gluon. They're all particles. And they carry forces, carry interaction. They carry verbs on their shoulder, okay? So what is a particle? Okay, so we look it up and it says a particle is a small localized object. Object. It's a thing. Okay, we got it. No problem. What's a physical object? All this from the Wikipedia, okay? Or physical body, or simply an object or body, okay, is a collection of matter. blah, 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 continues, right? Okay, so it's a collection of matter. So what is a particle? An object. What is an object? A collection of matter, whatever that is, okay? But it says particle, localized object, which can be described by several physical or chemical properties, such as what? Volume, density, mass, and they vary greatly in size and quantity. So we're talking about volume and size. So we are talking about a thing. At least that's what they're referring to, because they're talking about size and volume, take up space. So obviously they're talking about a ball or a cube or some object. That's what an object is. Okay, so all the definitions point to an object. How does this become a force? How does it become a verb, an interaction? This is where we have a little bit of problems in the language, and we have to settle this language because these people are contradicting themselves or coming up with total irrationality. Okay, so what is matter? I mean, if particle is a bunch of matter, or an object is a bunch of matter, what is matter? Okay, so Einstein tells us, occupies space and has mass. Okay, so what is mass? Well, he says mass is quantity of matter. So we have a circular definition. Matter is mass and mass is matter. Great, we learned a lot. Okay, one is the quantity of matter and the other one is a bunch of mass. So these are the scientific definitions, the mathematical physics definitions that we have today. Mass is matter, matter is mass. Great. How do we do it under the universal movie? Universal movie, again, is imagine cross-section of time, cross-section of motion. We're talking about zero motion. We're talking about location, a static concept. Nothing moves. So God freezes the universe. Everything is at a given distance from everything else. Just a snapshot. He just took a snapshot and gave us the snapshot. Do you see anything moving in that snapshot? It's a 3D snapshot, by the way, because everything's there in the universe, okay? Everything has a certain distance with respect to everything else, meaning everything has separation with everything else. Every atom in the universe with respect to every other atom. All atoms are a given location in that photograph with respect to everything else. Universal movies is just a bunch of photographs, bunch of locations of every object as they occupy different locations. They move from one location to another. Okay, and then we call the series of locations, we call that motion. But here we're looking at a single frame in the film. Okay, what do we see in a single frame of the film? Well, hopefully we don't see anything that's moving in there because it's a single frame. And so where do we put these words such as field and all these good words like particle and object and so on? Well, we're on record saying that object is a static concept. You don't need to have anything moving in order to define the word object. Object just that which has shape, which is also a static concept. Okay, particle, if it's an object, and usually the word particle refers to an object. In rational science, when everybody says particle, everybody thinks of maybe a little speck of dust, a little ball, a small, tiny speck of dust or ball or grain of sand. That's what a particle is. That's what we call a particle in science. Now, the mathematicians have distorted this word because they say, look, a particle is not a particle. It's not what you think a particle is, meaning it's not a corpuscle. And what do they mean? Well, they mean it's one of those quantum things where, well, we don't really know what it is because it's a vibration of a field and all this other good stuff. No, that's not the way it works in science. Particle is a corpuscle, just like Newton thought about it, okay, and everybody else before the 20th century. Everybody thought of a particle as a speck of dust, and therefore it's an object. It's a static concept. We do not have to have anything moving in order to understand what a particle is. So you can't say it's a vibration of a field, like they say today. Where do we put the word force? Well, force obviously is a verb. It's not a noun for the purposes of physics. It's a verb. Force means pull or push, just like good old Einstein told us. It's a push or a pull. Force means someone wins the tug of war. Okay? And so the question is, can we reconcile the word particle, which is the carrier of force? What does that mean? Is a particle a force a particle? Obviously not. Particle is an object, it's a ball, think of it as a ball, and force is what a ball does. Okay, so force is not an object. But they treat it as an object because they say, oh, it carries the force, it carries the interaction. So it's carrying a verb. Yeah, and all that's irrational. We don't use that language in science, we don't use it in physics. Okay? So force, very simple. Force is a verb. It's pull or push. Pull and push are both verbs. Someone wins the tug of war. We don't care about the equation, force equals mass times acceleration, or gravitational constant G, mass divided distance squared. We don't care about any of that. That's a description. We want to know what the definition of the word force is. The word force is a verb for the purposes of physics, just like the word motion. It's not a noun, it's a verb. Okay, the word orbit is a verb, not a noun. Okay, all these words are verbs for the purposes of physics. So force, pull, or push, it can't be a particle, can't be a synonym of the word particle. So to say that particle is a force, like, you know, the gluon is the particle of attraction between quarks, that's irrational. Either it's a particle or it's a force. And if it's a force, you got to identify what's doing the forcing, what's doing the mediation, what is carrying out the activity. That's what you got to identify. And of course, they can't do it with in quantum mechanics because, you know, they deal with something else. They deal with measurement and they deal with equations and not with physical interpretations, meaning qualitative explanations for how the subatomic world works.